We're now going to consider a couple of special cases for that straight current carrying filament. The first is going to be our infinite filament, and the second our semi-infinite filament. And in both of these cases, we're going to start with the expression we got from the previous video for our finite straight filament. And so we see the H expression as well as our U of phi direction shown there. So let's start by discussing our infinite filament. So I've got some I in a filament, and we can see it's extending forever on both ends, and some observation point P over here to the right. So first of all, let's talk about the impracticality of this. Of course, we don't have an infinite filament, so why are we even bothering looking at this, you might be asking. And that's a very valid question. But as we talked about with our infinite line charge, if our infinite filament length, or let me take a step back, if our filament length is, of course, finite, but it's really long compared to the distance between our observation point and the filament itself, then this might be a good approximation that saves us a lot of work. So let's talk about how we can adapt this equation from the previous video to this special case. And so ultimately it's going to come from our two endpoints. So remember previously we had some endpoints B and A, so it was starting down here at A and going to B, and we had written these position vectors from each of the 2 points. So we had something like this, and so for B we had an alpha 2, and so to point A we had some angle alpha 1. And so remember these were defined in this way such that the angles are sort of going downwards if the current is going up. Okay, so now we're saying that this is an infinite filament though. So instead of being at some finite point B, our end point is going to be at 0, 0, infinity, sort of implicitly assuming that this is still along the z-axis, and our starting point is going to be at 0, 0, negative infinity. So what we can think about doing is taking this line segment and just moving this up this line, and so of course what we can see is eventually that angle theta, or sorry, not theta, our angle alpha 2 is going to be going towards 0 as we're moving that up to our point 0, 0, infinity. So we can say that this is going to correspond to some alpha 2, which is equal to 0 degrees. Similar thing for our line corresponding to our start point. So as this is going to 0, 0, negative infinity, what we're going to see is that alpha 1 is going to become 180 degrees. So over here, this is going to correspond to our alpha 1 being equal to 180 degrees. So now all we need to do is come back and plug into this equation from the previous video. So we can see with our theta 2, or sorry, I keep calling it theta, with our alpha 2 being equal to 0, this is going to go to 1, and with our alpha 1 being 180, this is going to be negative 1. So minus and negative 1 is going to be adding 1, so we'll have 2. 2 divided by 4 over here is going to reduce that to just a factor of 2 in the denominator. And so we can write an updated expression for this special case of an infinite filament as H is equal to I, the current in the filament, divided by 2 pi rho in our phi direction. And again, keep in mind that our rho is still the perpendicular distance from the point of observation to our filament, and our phi is our locally defined phi direction, which is U of L cross U of rho. So that's our infinite filament. Now let's talk about our semi-infinite filament. And so you might be asking yourself, what's the difference between semi-infinite and infinite? And so again, it's sort of a weird mathematical thing. Of course, it's going towards infinity in this direction, but now we're saying it's not going towards infinity down here, so it has some finite start point. So let's say that it's starting at some point 0, 0, 0. Again, we're assuming this is going along the z-axis such that we can say the endpoint is going to still be at 0, 0, infinity, like we saw with our infinite line. It's very important when we're considering this semi-infinite filament that our point P is sort of quote-unquote lined up with the bottom or the starting point of our filament. And so what this means is that our perpendicular distance is actually just the distance from P, our point P, to the bottom of that filament, as we see here. So if we have that condition met, then we can sort of do the same thing. So now we have our A here, and so what we see is, of course, the axis of that current, the axis that that current carrying filament is on is going to be extending here, such that we can define our alpha 1 here. And so at point 0, 0, 0, our alpha 1 is going to be equal to 90 degrees. Same argument before though, if we considered some finite endpoint at B, we had some position vector that looks like this with some angle alpha 2. Well, now if that's going towards infinity, eventually that angle alpha 2 is going to be going towards 0. So alpha 2 is going to be 0. So again, we just go back and we plug into our equation. So our cosine of alpha 2, cosine of 0 goes to 1. And now we have cosine of 90, which is going to 0. So now we just have this factor out front, I over 4 pi rho. So let's come down here and write our equation for our semi-infinite line. So h is equal to I divided by 4 pi rho in our phi direction. So again, it's very important to use this semi-infinite filament case, or this semi-infinite equation. We need to have this p be lined up, so quote unquote lined up with the bottom of our filament. Another very important thing when using any of these equations is remember that our rho and our phi are locally defined. So that's true in these special cases as well. So our rho and phi are locally defined. Rho, of course, being the perpendicular distance from our filament to our point of observation. And our phi, our unit vector in the phi direction, is defined as u of L cross u of rho.